I'm going to make this video as a response to this one that was posted by the Action Lab on wave particle duality experiments. And I just want to state that I got a lot of respect for this guy. He has a very organized way of explaining how things are, and like his explanation he did for global wireless power, comparing the Earth to like a ball of liquid or something like that. That was really well done, I thought. But in this video, I have a lot of disagreements, and I'm going to explain what I disagree with and why I disagree with it by stating what I think is going on, or what I'm pretty sure is going on. And yeah, here we go. I'm not sure what this gentleman's name is, but good explanation. Good way of explaining things he has.
But here's the weird thing about glow-in-the-dark materials, is that in order to knock this electron to a higher energy level, all types of light don't do it, but it takes a specific color of light to do it. So for example, if I shine red light on this glow-in-the-dark material, no matter how strong of light I shine on it, the electron won't get knocked up to the higher energy level.
Yeah, see, that does make sense, because the red light is at a lower frequency than the green, potentially green glowing material you have here. If you try to shine a lower frequency than the potential frequency of the glowing material, you're not going to get any transfer of energy. It's in order to get this to glow, it glows at a green wavelength of light, or the green frequency part of the spectrum. You'll never get a higher frequency from red light to green light, because red is lower than green. That's why you're not going to get the glow-in-the-dark material to glow, because red is at a too low of a frequency.
Nothing. No charge whatsoever. But if I shine just a very dim blue light on it, the electrons will get knocked up to the higher energy level, and you can tell they did because they eventually glow and re-emit the light.
Yeah, blue light is at a higher frequency level than green. So the blue light coming in at a higher wavelength than the potentially green glowing light increases the energy state of the particles to their green glowing radiant level.
So what's weird about this experiment is that it disproves that light is a wave. Because if light were a wave, all you would need is very high amplitudes of a specific light, and eventually you'd be able to knock electrons up to the higher energy level.
Yeah, see, I'm not quite sure. See, he did say a wavelength, a high amplitude of a specific wavelength of light, which is correct, but his example was to use red light. I don't think I don't know where you got this concept, but if you have you can't have high amplitude of red light and get a potentially green glowing particle to get to its radiant energy state level. You need to have higher frequency, not higher amplitude. I mean, you did say specific wavelength of light. It has to be at a higher frequency. You see, whatever potential the particle that you're trying to shine light onto, whatever potential color it is, that's the frequency that the particle must reach in order to radiate or emit an electromagnetic wave. If you're shining a red light onto a potentially green glowing light, you're never going to get that green glowing light to radiate with the red light, because it's at a too low of a frequency. Even if you had massive amounts of powerful red light, it'll never get the green light to glow. Because the reason this is because the electrons are orbiting the nucleus at a specific orbit, and when they're at a high orbit, they're not glowing. But and they're at a lower frequency because they take more time to go around or to make their orbit, so they do less orbits than if they were at a lower orbit. So when the light waves come in at a higher frequency, that makes the electron go into a higher energy state or a lower orbit. And when it's at a lower orbit, it's it's at a higher frequency or a higher energy state. It's at the same speed that it was before. The speed doesn't change, but as its orbit size changes, its frequency, the amount of orbits it does in the same amount of time, goes up. So that's how you get a higher frequency wavelength coming in. You'll make the orbit of the electron go lower, and if it gets to a low enough orbit, it'll begin to radiate its color, whatever specific color wavelength it radiates at. So you have to have higher frequency in order to get a particle to go to a lower orbit and emit light. And if that wavelength stops colliding with the particle, it'll slowly go back to its higher orbit, or the lower frequency, the lower amount of orbits it makes at the same amount of time, it'll make less of them at a higher orbit, so that means it's at a lower frequency, and it'll stop radiating. I don't know where he got this idea that you can use high amplitude waves to make a particle jump to a higher frequency rate, because that's not correct. You need higher frequency to make because these electrons are already in motion. They're just at specific orbits. And if they're at too high of an orbit, they won't radiate. And in order to get them to a lower orbit, you have to energize them with a higher frequency wavelength of light. You have to collide a higher frequency wavelength of light onto them to get them to do that.
But what I'm telling you, that even if you had enormous amplitudes, extremely high intensity of red light, you still couldn't knock this electron up to a higher energy state. But even with a very, very, very dim blue light, you would be able to knock it up to the higher energy state. So an experiment similar to this one, called the photoelectric effect, is what led scientists to develop the field of quantum mechanics. And what they said is that light actually isn't a continuous wave like this, but it's actually made of discrete particles. And those discrete particles have specific momentums. And in order to knock an electron up to a higher energy state, it has to be hit with a particle that has enough momentum to knock it up to that higher energy level.
Okay, you see how he just explained that? The quantum mechanic theorists say that a light. Well, okay, it's hard for me to say this because I know in my mind it's not correct, but a light is a packet or particle that comes in and collides with other particles to get them to go into a higher energy. Like if they were billiard balls or something. And that's not what's happening. Like this electron is in motion. It's going in a circle around its nucleus at a specific orbit. And the way he said it just now, it makes it sound like everything is like little marbles that are flying around, and as these marbles come in and collide with the marbles of the atom, then it makes them speed up. It's just like that. That's not what happens. That's like in billiards where you have a ball at rest, another ball come in that's moving and it collides with it, then it stays at rest, and then the other one starts to move. I mean, that's not how particles work. I've never really agreed to these ideas these theorists have in quantum mechanics. Like quantum mechanics and all the ideas in quantum mechanics, to me, literally make no sense whatsoever. And I think this is why. It's because they're building their ideas on false concepts. This is not a valid concept that a light is a particle coming in and colliding with other particles. That is not correct. And they're building their quantum mechanic ideas based on that. So when you do that, you're sending yourself down a imaginary rabbit hole that's going to lead to ideas that have no connection to reality, because you made a false assumption here. It's like if you build your ideas on invalid ideas, then you're going to just end up with a series of ideas that are not even correct or have no connection with reality.
And that makes sense, right? Not just any particle can hit it, but it has to have one that has enough momentum to knock it up there.
Momentum? See, how does that make sense? A particle has to have enough momentum to knock the particle to... That's not what happens with light. Light is at frequencies, not momentum. All the particles are at the same speed. They're just orbiting at specific orbits. The lower the orbit, the higher the frequency, the same speed, but the lower the frequency because the lower the orbit. Higher the orbit, the lower the frequency, but it's at the same momentum. And when a wave comes in, light wave comes in at a higher frequency, it'll push the particle into a lower orbit, making it go into a higher energy state, and thus making it glow. So I'm just going to stop it right there because I don't want to keep dogging on this guy's video because he does a lot of great work, but there's a lot of videos on wave-particle duality out there, and all these vast amounts of ideas that are being generated by, and they're built on these incorrect concepts. And this is why we're not progressing in science at all. Like this kind of stuff was studied back in the 1930s, almost 100 years ago. And we still haven't moved forward in our research with light because we're building our ideas on these false assumptions or incorrect or invalid concepts. And that's why all of our ideas since then have basically not gotten anywhere. So I'm not sure if anybody else is thinking the same way I do, but particles are not in motion, or not transferring momentum. They're transferring energy in the form of a electromagnetic wave being emitted by glowing particles. Glowing particles emit electromagnetic waves out into space, and when they collide with other particles at a lower frequency, they go into a higher energy state. An energy transfer happens at that point when the waves come in at a higher frequency and make them go into a higher energy state. That's the concept of how electromagnetic waves interact with particles, or how particles interact with each other at a distance by emitting electromagnetic waves and having those electromagnetic waves collide with other particles. As they collide with other particles, they react to it and they build their energy state by going into lower orbits. Not faster momentum, lower orbit, less amount of orbits than at the same amount of time as before, thus higher frequency. Okay, so with all due respect, the Action Lab, keep up the good work, but I need to disagree on your thoughts here on wave-particle duality.